Hello, welcome back to the channel. So let's continue our discussion on comparison test and check whether this improper integral converges or diverges. So in this question, what we will do is we'll use all the concepts that we learned about the comparison test and assume a second function for which it is easier to calculate the integral of our second function as compared to this first function over here. Because if we try to evaluate this integral over here, we'll have to use some complex methods in order to evaluate this integral over here. So that is why we'll come up with another function for which it would be easier for us to calculate the integral for. And now you know that in comparison test we basically have two cases. So in the assumption of the second function, if we want to prove that this integral converges, we will have to assume one function which is always greater than our original function over here, right? For the interval specified in the definite integral. And if we come up with a second function which is always greater than the first function, and we know that the second function converges, then our this function would also converge, right? But on the other hand, if you want to prove that this definite integral diverges, you'll come up with a second function which is always smaller than the original function, and if your second function diverges in this case, then you'll prove that your original improper integral will also diverge, right? So these are the concepts that we already know about the comparison test, and we already covered these concepts in the last videos. So I'll highly suggest you to first watch those videos in order to get the full idea about this question over here. So now you can clearly see that we have to come up with our g of x function for the comparison test, and our f of x function is basically, so you know that our f of x function is basically 1 over root 4x square minus x in this case, right? Which you can clearly see over here as well, right? So this is your fx function, and now you have to come up with a second function for which it is easier for you to calculate the integral of that second function as compared to this function over here, right? And we can clearly notice that by comparing this function, if we have another function which is much more simplified, which has its denominator much more simplified, for example, the denominator is something like 1 over root 4x square, right? Which is indeed equal to 1 over 2x. We know that it is much easier for us to calculate the integral of 1 over 2x as compared to this function over here, right? And this second function also simplifies our first function over here, right? 4x square minus x, I can simply remove the minus x to make this function simpler and come up with our second function. So now, based on comparison, we can clearly see that we can come up with the second function, which is 1 over 2x in this case. And now, since we have to compare these functions first, we can clearly see that 1 over root 4x square minus x is always greater than equal to 1 over root 4x square for the interval specified in the definite integral. You know that since our interval is from x equals 1 to x equals infinity, and since in this case, if we compare both of these expressions, the denominator on the left hand side is smaller than the denominator on the right hand side. So if the denominator on the left hand side is smaller, that means the original expression on the left hand side is greater than equal to than the original expression on the right hand side, right? And that is, so this expression is basically also equal to 1 over 2x in this case, right? Which is our second function over here. So we know that 1 over 2x is always less than equal to our original function over here. And if that's the case, if our g of x is always less than equal to f of x, we just have to prove that our g of x dx integral with the same endpoints diverges. If we are successful in proving that, then we'll also prove that our original function will also diverge. So let's try that. Let's try to calculate, since we are concerned with the integral of g of x dx from x equals a to x equals infinity, where our gx is basically 1 over 2x dx, our a is 1 and infinity is the same value, right? So now if we calculate this definite integral and conclude that this definite integral diverges, we will also conclude that our original function will also diverge. So we know that when we try to calculate such improper integrals, what we do is we take limit capital R approaches to infinity, 1 to r 1 by 2x dx, and then you know that you can take the constant out. So let's take the 1 by 2 constant out of the limit. It would be 1 by 2 limit capital R approaches infinity integral 1 by r 1 by x dx, and then you know that the integral expression would basically be ln x with the endpoints 1 and r, and then substituting the endpoints into the integral, you'll get ln mod r minus ln 1 in this case. And you know that since ln 1 is 0, if you take the limit of r approaches to infinity, for this expression over here, this expression will approach ln infinity, which is infinity. So your whole integral, which is this one, your solution to this integral will be infinity, which means that your definite integral of this expression diverges, right? Since we proved that this definite integral does not have a real solution to it, we know that our gx dx integral diverges. And since that is the case, since g of x dx integral diverges, based on the comparison test, our f of x dx integral, which is this original integral, also diverges. And that is what we proved only by using the comparison test. So as a basic summary of what we did in this video, we came up with a second function for which it was easier for us to calculate the integral for. And then for the second function, what we did was first compare both of these expressions so that we can match the cases related to the comparison test. And after matching the case related to this comparison test, we concluded that our comparison of g of x and f of x is similar to the case 2 over here. So since our information matched the case 2, we just had to prove that this integral diverges in order to also prove that our original integral also diverged. So that's it for this video. Again, feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.